6 days ago, you had never opened Grasshopper. Today, you're going to build this. A complete parametric pavilion, twisting ribs, a ribbling bloom, a nested inner layer, spiral openings, a double shell roof, 12 sliders, infinite variations. Let's build it from scratch, step by step. I am Ajit Kumar. This is day 7, the phase 1 final project. Welcome to your first real Grasshopper project. Today is different from every other day in phase 1. Almost everything we use today, the curve parameter, divide curve, plane normal, circle, extrude, you already seen. There are small number of new components too. Sine, multiplication, arc, deconstruct plane and loft. Each one is simple and I will explain exactly what it does the moment it appears. Nothing here requires anything beyond what you already know. Today's job is to put all of it together into one cohesive architectural object with real visual presence. By end of this video, you will have something you could genuinely put in the portfolio as your first computational design project. Let's go through a build sequence. 10 steps, 1 pavilion. Step 1. The spine curve. In Rhino, click in the command bar and type interp curve, press enter. Click 6 to 8 points to define a flowing S-curve, something with one gentle blend, not a straight arc. This gives the pavilion a much more dynamic silhouette than a simple arc. Press enter when you are happy with the shape. There is our spine, the backbone of the pavilion. Now in Grasshopper, place a curve parameter. Right click the curve parameter. Select set one curve, click the spine in Rhino, press enter. The curve parameter turns grey, data loaded. The spine is now inside Grasshopper. Step 2. Divide the spine into rib positions. Place a divide curve component. Connect the curve parameter output to the C input. Place a number slider. Set it to integer type, range 6 to 40, default 16. Label this slider rib count. Connect it to the end input of the divide curve. Look at Rhino. Red cross appears along the spine at equal intervals. 16 rib positions, equally spaced along the spine. Remember, divide curve gives us 3 outputs here that we are going to use for 3 different jobs today. P for position, uppercase T for orientation and lowercase t for driving both the twist and the bloom. Step 3. Orient the plane so our rib stands perpendicular to the spine. We need plane normal. Connect the P output of divide curve, the division points, to the O input of the plane normal. Connect the uppercase T output of divide curve, the tangent vectors, to the Z input of plane normal. The planes are now oriented perpendicular to the spine at every division point. Ribs built on these planes will stand across the spine exactly as they should in the real rib structure. Step 4. The twist. Instead of rotating every rib at a flat, constant rate, we are going to ease the rotation, starting fast and settling gently towards the far end. That single change is what separates a mechanical spiral staircase from an elegant flowing twist. Place a number slider, range 0 to 1080. Default 360. Label it twist amount. This is the total rotation in degrees from the first rib to the last. Notice the range and default are both much bigger than the modest beginner version. A shy twist is exactly what makes the pavilion looks overwhelming. Now the easing. Place a multiplication component. Connect the smaller case t output of the divide curve to input A. Connect the number slider fixed at the value 1.5708 that pi over 2 to input B. Place a sine component. Connect the multiplication output into it. Call this output your ease curve. At the start of the spine, t is 0. So this gives sine of 0 which is 0. At the end of the spine, t is 1. So this gives sine of pi over 2 which is 1 the maximum. But because sine flattens out as it approaches its peak, the rotation speed is fastest near the start and gently decelerates towards the end, instead of spinning at the one rate the whole way. That deceleration is what reads as elegant instead of mechanical. Now place a second multiplication component. Connect your ease curve to input A and the twist amount slider to input B. This gives you the actual rotation angle in degrees for every rib, easing smoothly up to the fully twist amount. Exactly like day 4, Grasshopper needs radians, not degrees. Place a radians component and connect this multiplication output into it. Now place a rotate component. Connect the plane normal output, the unrotated perpendicular planes, to the G input. Connect the radians output to the A input. And for the P input, the rotation axis, connect the same plane normal output again. Feeding the plane itself into P means each plane rotates around its own center and its own normal axis, exactly like spinning a coin in place. Call this output your outer twisted planes. We built on it for the rest of the pavilion. Now here's the move that adds real architectural depth. a second independently twisting layer nested inside the first. Place a number slider range 1 to 3, default 1.8, label it inner twist multiplier. Place another multiplication component. Connect the twist amount slider to input A and the inner twist multiplier slider to input B. This gives you a larger total twist value for the inner layer. For example, if twist amount is 360 and the multiplier is 1.8, the inner layer will complete a full spin of 648 degrees. Place one more multiplication component. Connect your ease curve to input A and the output you just made to input B. Then the degrees to radians. Then a second rotate, same setup as before. G and P both from the original unrotated plane normal output, A from this new degrees to radians. Call this output your inner twisted planes because it twists at different total rate than the outer layer. The two layers will spiral past each other at different speeds once we build ribs on both, our inner structure winding through the outer one. That relationship is what starts to give this pavilion real architectural presence. Step 5. Instead of one plane smooths well from narrow to wide and back to narrow, we are going to layer two sine waves together. So the radius ripples rhythmically along the pavilion, much closer to how the real structure rip pattern works. Place two number sliders, minimum radius, range 0.3 to 2, default 0.5. Maximum radius, range 1 to 7, default 4.5. Notice the gap between these two is much wider than before. More contrast between narrow and wide is a large part of what reads as dramatic rather than modest. Now place a multiplication component. Connect the divide curve lowercase t output to input A. Connect the number slider locked to the fixed value 3.14159 which is pi to input B. Place this sine component and connect this multiplication output into it. This is your main blow. 0 at the start, maximum in the exact middle, 0 at the end, exactly like before. Now the ripple. Place a number slider, integer type, range 1 to 6, default 3. Label it ripple frequency. This is how many extra small waves run across the bloom. Place another multiplication component. Connect the same lowercase t cross pi output you already built, the one feeding your main bloom sine into input A. Connect ripple frequency into input B. Place a second sine component and connect this output into it. Call this your ripple wave. It swings between -1 and 1 and completes several full cycles across the pavilion instead of just one. Now we turn that ripple into a safe multiplier that only ever makes the bloom a little narrower. Never inverts it, never goes negative. Place a number slider range 0.3 to 0.95, default 0.6. Label it ripple flow. Place a construct domain component, connect ripple flow to input A, connect the number slider locked to the fixed value 1 to input B. Place a remap number component. Connect your ripple wave into V. Right click the source input and set it to the domain of -1 to 1 that matches what sign outputs. Connect your new construct domain into the target input. Call this output your ripple factor. It always sits between your ripple floor and 1, so it can only ever gently reduce the bloom, never flips it upside down. Now, place one more multiplication component, connect main bloom to input A and ripple factor to input B. This combined bloom signal is a rhythmic 0 to 1 value, mostly following the big signal swell of main bloom, but it's several smaller ripples running through it from a ripple wave. This is the one signal that is going to drive radius, thickness and opening size, so everything on this pavilion pulses to the same rhythm. Place a construct domain component. Connect minimum radius to A, maximum radius to B. Place a remap number component. Connect combined bloom signal to V, a fixed 0 to 1 domain to source and your new construct domain to target. That is your final radius, the number that will drive the outer rib size at every point along the pavilion, rippling and swelling instead of moving it one flat curve. Let's do the same thing for rib thickness. So the structural depth tapers with the same rhythm instead of saying one flat value. Place two number slider. Rib thickness minimum, range 0.03 to 0.15, default 0.11. Rib thickness maximum, range 0.1 to 0.5, default 0.22. Place a construct domain, rib thickness minimum to maximum, and a remap numbers exactly like you just did for radius. Combine bloom signal to V, 0 to 1 into source, and the new construct domain into target. Ribs will now be thicker where the pavilion blooms wide and finer where it narrows. A small detail, but it's exactly this kind of tapering that makes a structure reads as considered rather than generic. Step 6. Two things happen here. We open each rib into a spiraling arc instead of a closed ring, and we built a second nested inner layer of ribs that twisted as its own rate instead of the outer one. This is the step that gives the pavilion its layered wow factor depth. First, the fix. Place two number sliders, opening angle minimum range 40 to 180, default 90. Opening angle maximum range 200 to 355, default 320. Both are in degrees, human friendly numbers. Place a construct domain, opening angle minimum to maximum, and a remap numbers, combine bloom signal into V, 0 to 1 into source, and the new construct domain into target. This makes the opening size follow the same rhythm as the radius. Wider openings where the pavilion swells, narrower where it tapers. Now place a radiance component and connect the output into it. Then place a construct domain, fixed value 0 into A and the radiance output into B. Place an arc component. Connect your outer twisted planes to its P input, your final radius to its R input, and your new outer angle domain to its A input. Now the inner layer. Place a number slider range 0.3 to 0.75, default 0.55. Label it inner radius ratio. Place a multiplication component. Connect final radius to input A and inner radius ratio to input B. Call this inner radius, always a proportional fraction of the outer radius, so it automatically stays in sync with the bloom without any extra wiring. For the inner ribs, we want them to read as nearly solid rings, a visual contrast against the dramatic open gaps of the outer layer. Place a number slider logged to the fixed value of 345, label it inner opening angle fixed degrees. Connect it through its radians, then into a construct domain with a fixed 0 in A. Now place a second arc component. Connect your inner twisted planes to P, inner radius to R, inner angle domain to A. Step 7. Give both layers real structural depth. Because every rib is individually twisted, we cannot extrude along one fixed world direction. Each rib needs to be extruded along its own local direction. Place a deconstruct plane component. Connect your outer twisted planes into it. We want its Z output, the local outward direction for the outer layer. Place an amplitude component. Connect the deconstruct plane Z output to V and the final thickness value from step 5 to A. Place an extrude component. Connect outer arc to B and this amplitude output to D. Now repeat the same three components for the inner layer. Place a second deconstruct plane fed by inner twisted planes. For the inner thickness, place a multiplication component. Connect final thickness to A and the number slider log to 0.6 to B. This keeps the inner ribs visibly finer than the outer ones, which reads as more delicate secondary structure nested inside the bolder primary one. Place an amplitude. Connect the inner deconstruct plane Z output to V and inner thickness to A. Place an extrude. Connect inner arc to B and this amplitude output to D. Look at Rhino. Two fully independent structural layers, each with a correct local extrusion, each tapering with a bloom. This is the real considered structural system, not a single row of identical rings. Step 8. The roof. We are going to loft both layers separately, using the arc from before extrusion to get a genuinely double shell canopy and outer skin and a second nested inner skin visible through the spiral openings. Place a loft component. Connect your outer arc output, the full list of outer ribs curves, into its curve input. Loft takes an ordered list of curves and builds a single surface that flows through all of them in sequence, like stretching fabrics over a series of hops. Because our arcs are already ordered along the spine, lofts connect them correctly on its own. Now, place a second loft component. Connect your inner arc output into its curve input. That's our complete pavilion design. That's the power of parametric design. The design system generates form, you guide the parameters. Phase 1 is complete. 7 days. You went from never having opened grasshopper to building a twisting, blooming, portfolio ready parametric pavilion using a correct Rhino 8 components the whole way through. Save your file, name it day 7/pavilion. Keep it, this is your first real project of this computational design. Phase 2 starts tomorrow, and Phase 2 is the most important phase in this entire 60-day course. We are going to study data trees, list of lists, the concept that causes 80% of all grasshopper errors. And once you understand it, you will never be confused by a grasshopper error again. Subscribe so you do not miss day 8. Post your pavilion screenshot in the comments. I want to see all three variations. Show me minimal bloom, dense spiral, and a wide window. No two will look the same. See you in the phase 2.